So we are ready for the last talk. Thank you very much for staying with us till the very end. It gives me a great pleasure to introduce Adolfo Guillot, who has a very nice trajectory within this CNRS CONACyT development. He went to l'École Normale Supérieure de Lyon to work with the PNGs, who was a good collaborator of Alberto Berkowski, and now he just returned from a sabbatical stay in Paris with Bertrand Delroy.
Okay, thank you, Javier. Okay, so thank you all for staying until this time. So I would like to tell you about these some complex differential equations without multi-evaluation in their solutions. I like to just give a rough motivation for these themes and then just state one result with Giulio Rebello from Toulouse. So let me consider this a system of ordinary differential equations. That's the system known as Euler's stop. So this is a system of equations that comes from physics. So you want to understand how things rotate in space. So you begin with something that's not very symmetric, say some potato. And then before understanding anything else, you suppose there's no gravity. So there's just this potato turning in space. And you want some equations that describe how does this potato move in space. So that's what Euler's equation do. These are three variables, omega 1, omega 2, and omega 3, that are the components of the angular speed with respect to a system of coordinates fixed with the rotating body. And then, as far as the rotation is concerned, you only need to know three quantities about the body, which are called the moment of inertia, that are called I1, I2, and I3. So the equations are I1 times omega 1 prime is I2 minus I3 times omega 2, omega 3, and the cyclic permutations of this equation. So it's quadratic, it's homogeneous, and so this happens in R3. So you have some equilibrium point at 0. And then there are two conserved quantities. One of them is energy. It's the sum of the squares of omega 1, omega 2, and omega 3. So in R3, if you think of the orbits of this equation in R3, they are all staying within the surface of a sphere. Santiago?
I don't see omega 1 on the right side.
Because so it's omega 2, omega 3. This is omega 3, omega 1, and omega 1, omega 2. Okay, so there's one first integral, that's energy. So the orbits stay within the surface of a sphere. And then there's a second first integral, that's the angular momentum seen from the original space. And the level surfaces of that second first integral are ellipsoids. So motion takes place, each orbit takes place in the intersection of the sphere and of an ellipsoid in general. So it's some closed curve. I won't even draw it, but you see what it is. It's the intersection of a sphere with an ellipsoid. Okay? So the system is completely integrable. James talked about some integrable systems. But in fact, and if you want to see what are the equations, the actual functions that solve this system of differential equations, you can calculate and see, for example, that omega 1 prime, if you square it, is some degree 4 polynomial in omega 1. And this polynomial has coefficients which are constants, which can be expressed in terms of these conserved quantities. So Euler didn't know how to solve this equation, although he knew a lot of things. We had to know, to get a true feeling of what these equations, what the solutions of these equations are like, we need to wait until Gauss and Jacobi to understand the elliptic functions, and also pass to the complex plane, so the complex variables. So let me consider this system of differential equations not as variables, as real variables of a real, as real functions of a real variable, but as complex functions of a complex one. So if I make the same drawing, then in C3, I have two quadratic equations. So the level surface will be some affine curve. So this affine curve will be a puncture torus. We'll have 4 punctures. And within each one of these elliptic curves with this one-dimensional complex tori, I have a complex vector field, which is the natural vector field that one has in C mod lambda, where lambda is some lattice in C. So you have the translation invariant natural vector field in C, and you can put in this elliptic curve, in this torus. So C3 is filled up with these curves, and that's the motion. So you'll agree with me that this picture on the right-hand side, having a torus and having a vector field, is much more rich than the one in the just real, where we don't really see what's happening with the orbits. So that's one motivation for going to complex variables. There's a lot of equations in physics that involve elliptic functions, like the ones we are considering. And so one of the motivations to consider this complex differential equations comes from the realm of integrable systems. So people that study integrable systems are like butterfly hunters. So they spend a lot of time looking for some precious differential equation, and then they collect it, and then they admire it, and then they admire it, and then they look for other equations. So, and complex variables is a nice way to go hunting for integrable systems. So there's another family of classical systems, integrable ones, that comes also with tops, now with heavy tops where gravity is concerned, and they saw the Kovalevskaya tops. So so going to complex variables has a drawback, and the drawback is that complex functions are very easily multivalued. Take, for example, the logarithm function. So the exponential is not injective, not one-to-one. The inverse, the logarithm, has some multivaluation, and this multivaluation will be present in most solutions of differential equations. So that's one drawback. So we have Kovalevskaya stops, which is analog to it's a rotating body, but it's a heavy, and then she concentrated on the following fact is that integrable systems, or the solutions that solve integrable systems, are not multivalued. So one way to look for integrable systems is to look for equations that do not have multivaluedness. And then by following this approach, she found this integrable system known as the Kovalevsky top. And this involves defining some quantities that are sometimes called Kovalevsky exponents. So this is both an example and an illustration of what a Kovalevsky exponent is. So consider these differential equations in two variables, two complex variables. Z prime equals z squared, and w prime equals mu times z times w, where mu is some complex number. Okay? So you can integrate this equation. So z of t equals minus 1 over t. Its derivative is it's square. And then w of t, it's w0 times minus t to the power minus mu. Okay, so if this coefficient mu is an integer, this will be a true function. If this is a rational complex number, it will have as many local determinations as the denominator of your rational number, and in general, it will have infinitely many determinations. But you can also see this. If w0 equals 0, we have the equation, well, the solution, z of t equals minus 1 over t, and then w of t equals 0. So you can think of this as a perturbation of the solution minus 1 over t, 0, and this exponent is some sort of resonance coming into this perturbation. So in general, when you have some algebraic system of differential equations that has some sort of homogeneity, you can define this Kovalevsky exponents, and then there comes some, say, some conditions. There's some numbers that need to be integers in order for no multivaluation to appear in the solutions. So that's sort of the philosophy behind these Kovalevsky exponents that have been rediscovered many times. Many times. Okay, so chasing for integrable systems, well, so mechanics and the success of elliptic functions tells us that it's nice to consider complex differential equations, and some problems, for example, in integrable systems, tells us that it is a good idea to look for equations that do not have multivaluedness. So let me tell you about another setting where you do not want multivaluedness to appear. And that comes from the following thought of Painlevé. So he said, well, why? So many interesting physical, mathematical problems have a solutions. The solutions are given by linear differential equations. So what are linear differential equations, say, of the second order? Let us consider. So y, the second derivative of y, equals some function f of t times y prime plus some function g of t y. So if we think of it in the complex domain, and we have here the t-plane, we'll have some singularities, I don't know, concerning the poles of f and g. But then if I take one t0 and I fix it, and I think of all the initial conditions at this time t0, say this is giving a value to y at t0 and a value to y prime at t0, so I consider all the points above here. I may want to know how do these initial conditions evolve when I follow a path from this time t0 to some time t1. And this will happen since we have a linear differential equations, we have superposition, and this will be given by some linear map here. Okay, so very simple. You restrict your initial conditions in time t0. When you go to time t1, you advance by a linear transformation. So that's for linear equations. And now what happens for the equations like the one we were considering, y prime square equals some polynomial of y, say of degree 3 or 4? Well, you can consider the associated second order equation by derivating this, and this gives you that y, the second derivative of y equals 1/2 of p of y. So it's an equation that's not quite like the first equation we saw. It's a nonlinear equation, but for this equation we have some very similar phenomenon. You have, well, not here, you don't have singularities, but say you might have. So you pick some time t0, and you look at all the initial conditions above this time t0, and then you consider some other time, maybe a close time t1, and then you try to follow all this, the solutions, all the initial conditions from this set above time t0 to time t1. So here you will have a very nonlinear map. That's hard to say, how to describe. There will be some points that escape in some time to infinity, but it will be a well-defined map there where it is defined. So there's no multivaluedness in this map of advancing time t. So you start with something in time t, and you advance, you get some definite quantity in time t1. And this phenomenon is what Painlevé thought was behind all the successful equations in physics. This is nowadays called the Painlevé property. And is very much related to the absence of multivaluedness, the fact of being able to advance some time for a differential equation. Yes?
So instead of, by example, can you state the Painlevé property?
We can talk about that later. So it's hard to. Okay, so this is not. That's what I think. Painlevé thinks.
Okay.
Okay, so Painlevé said, so this is a very important property. Let's go ahead of time, and before the problems of mechanics arrive, let us have the solutions of the equations ready. So let us classify all, for example, the second-order equations that have this property and understand them so we're ready for the future equations that will come. So he embarked in this amazing program that Poincaré thought was an island isolated from the rest of mathematics. And so he was successful, and he wrote these 6 equations. Here are the first 6. Here you have the first 6. The first one is close to being the ones that give elliptic functions. So it's the second derivative of y. It's 6 times y squared plus t. If this t were absent, you would have some elliptic function. It's slightly different. And then there's other equations, and people talk about them like Painlevé 1, Painlevé 2, 3, 4, 5. And then the master equation is the Painlevé 6. So these are the functions, and these are functions that are related to the absence of multivaluedness when you go from some time to another, and that do not reduce to some previously known equations like linear ones or elliptic functions. So this is just for, in order for you to know these equations, and we don't really quite understand this classification. I don't really quite understand this classification. There's some people that, for example, if we replace, we have been here talking about equations that have some fiber, that's in this case the set of initial conditions of a linear differential equation. So this is C2. And here we also had C2. And in the Painlevé case, we have sort of C2 as the tangent space of C. So maybe we need to say a good test for seeing if we understand this classification would be to replace this C2 by some affine variety. And then can we do the same classification? Can we import what we know? What do we know really behind these calculations that we don't really know where they are going? Although I am exaggerating, there are some interpretations about these things. So we need to know, so this question about what if we replace, for example, this C2 by an affine variety, lead us to understand what are, for example, the differential equations given by vector fields on varieties or on complex manifolds and so on, whose solutions do not have multivaluedness. Okay, so that's another motivation. So let me state, so let me be precise on what I mean by not having multivaluedness a little bit. So this is C2, and then there's some very interesting classifications made by Chassis for equations of the third order, and that's around 1910. And we will see some of the Chassis equations later. So in general, when you have a function or an element of function, some function defined in some open subset of C, and you want to extend this function, you may try to consider the analytic continuation along some path, and then consider the function that results in getting this analytic continuation. And the absence of multivaluedness means that if I take a closed path and I take the analytic continuation along this closed path, then I return with exactly the same function that I started with. Otherwise, if I get some different functions, I have some multivaluation, because in this domain, I don't know if my solution is given by the first determination of my function or by the second one. So that's absence of multivaluedness. And one natural setting to try to understand this is consider differential equations or complex differential equations given by meromorphic vector fields on compact complex manifolds. For example, all of these equations are, the autonomous ones are of this kind. So you have some, or if you have some polynomial vector field in some variety in Cn, and you compactify into Cpn, you will add some poles at infinity. And so this is a good, so already we have some trouble in understanding this. And the general problem is understand the equations. This is the polynomial, the rational or meromorphic vector fields on compact complex manifolds. Understand this, the equations whose solutions do not have multivaluedness. And I'm not saying, probably these equations are not solved by functions defined in the whole plane. Maybe there are some singularities like the ones James was telling us about. So we also need to describe what happens. It would be good to know what happens to the solutions as we approach the singularities of the domain of definition of the function. Okay, so we have a very, very good understanding of this problem in dimension 2. Let me begin by stating a result that is, in some sense, some generalization of this of the combinatorics that comes with the Kowalewski exponents for meromorphic vector fields and surfaces. So this is following. This is part of a joint work with Giulio Rebello from Toulouse. Suppose you have a meromorphic vector field in a complex surface. The result is local around some component of the curve of poles, some compact component of the curve of poles. So suppose that your vector field does not have multivalued solutions, and then you have your connected component, compact of the curve of poles. So we can describe exactly what should this curve of poles be. This absence of multivaluedness imposes some restrictions in this curve of poles, and this description is the following. So what can happen is, for example, that this curve of poles is some rational curve, a sphere, or an elliptic curve, a torus, of vanishing self-intersection. That's one of the possibilities.
Your surface is compact?
No, this is just a local around this component of poles. I will say what this entails for compact surfaces in a bit.
But the curves of poles are compact?
Yes, the curves are compact. So
For the general problem, you have any restriction? Keller, Hodge, just general?
Well, so this is the general, since we do not have the solution of a general problem, you can, say what you can. So put the hypothesis. But the result, well, I'll state the result that has no hypothesis in that sense. So that's one of the possibilities. The other possibility is that your curve is not reduced. It has several irreducible components, all of them being rational curves. And when you have such a configuration of curves, you can attach a dual graph to that. So you put a vertex for each rational curve and an edge if two of them intersect. So the dual graphs, the admissible dual graphs, are these ones that you might recognize as the extended thinking diagrams. So it's not ADE, this is not ADE, but A tilde, D tilde, E tilde. And in fact, you can consider that the curves that are attached to these diagrams are in some sense degenerate elliptic curves of vanishing self-intersection in some way. These are the configurations that appear in Kodairo's classification of singular elliptic fibers for vibration. So when you put together this with many things we know about compact surfaces, you get this result. So it's mainly it's part of the joint work with Giulio in the Keller case, and you can extend it to the non-Keller case as well. So you take a compact complex surface with no extra hypothesis, and you take a meromorphic vector field in it, and you suppose that it has no multivalued solutions. So then up to some transformations that involve maybe blowing up and blowing down some points, you're in one of the following three situations. So either your vector field is holomorphic, And since holomorphic vector fields on compact manifolds are complete, your solutions are complete. The singularities you find in your original vector field are just poles, like in the case of the original Euler's top equations. So the second possibility is that X has the first integral, so that in general, so that you have some, so you don't really have a surface. Well, you do have a surface, but you can decompose your surface in curves, and the vector field will be tangent to each one of these curves. And so this is not really a two-dimensional system, but just a set of one-dimensional ones. And then the third possibility is that X preserves a fibration on your surface M. So it means that your surface fibers over a curve, and that if you take a generic fiber over fibers in the sense of so not a C-infinity fibration above most points, but by some holomorphic map, so that your vector field will be transverse to a generic fiber and will in fact map fiber to fiber, so that you actually have some vector field in the base. So this is in some sense like going from a two-dimensional or two-variable autonomous equations to a one-variable non-autonomous equation. Or if you want to put it in more algebraic terms, your differential equation, you can split it in two parts. There's first the differential equation you need to solve at the base, and then this will produce you some functions, and then your differential equations will be a first-order differential equations over this field of functions, intermediate. So sort of 1.5 degrees of freedom, not really 2, or separation of variables. Okay, so let me illustrate. I don't know if there's any questions about the statement. And we would like to have some ideas of what happens in dimension 3, but we only have very wild examples that we don't quite understand. That produce things that we don't understand. So let me give you an example that illustrates this result. Or maybe it doesn't. Let me just share an example that I like a lot. Okay, so this example comes from and I forgot to say that there's a related result. There's some intersection of this result and one previous result by Marco Brunella who classified complete polynomial vector fields in C2 after proving, using some results of McQuillan, that such vector fields preserve a fibration. So by either being tangent to it or transverse. Okay, so there's some intersection of the spirits and of the results. Okay, so let me come to this equation. This is the Chassis-9 equation. This is a third-order equation, and then it says that the third derivative of phi, say, it's a function of phi prime and phi squared, which is actually a polynomial with rational coefficients, integer coefficients, having degree 4 on phi and 2 on phi prime. So this is a very, it looks like a naive equation. And so you can write the vector field that's equivalent to it. And according to Chassis in 1911, this equation should not have multivaluedness. After doing this sort of Kovalevsky exponent analysis and some other analysis, he arrived at the conclusion that this should be one of the good equations, one of the equations that do not have multivaluedness. And so this is a third-order equation. It gives a vector field in C3, but it actually has a first integral of degree 10, polynomial equation of degree 10, that's constant. So actually, this equation, it's like one of the ones we're considering. You have a vector field in some variety. So according to our theorem, you should either find some way to compactify this into an equation, into a compact manifold where the vector field extends as a holomorphic one, or find some fibration or some first integral associated to it. So let me describe what the integration of this equation leads to according to Cosgrove, who did this in around the year 2000. So let me come to so the answer will be it extends as a holomorphic vector field to some manifold, and I will tell you what manifold and what vector field it is. So okay. So consider in C2 the lattice generated by this. You take a fifth root of unity, and you consider the following 4 points in C2. You consider the points, if you say zeta is the fifth root of unity, you consider the points 1, 1, zeta, zeta squared, zeta fourth, zeta cubed, zeta. And this generates a lattice. And this lattice has an order 5 symmetry, generated by multiplying by this 2 by 2 diagonal matrix zeta, zeta squared. So you can see that it actually preserves the lattice because you can see that the generators are mapped into linear combinations with integer coefficients of the generators. So you can quotient C2 by this lattice. It will give you an abelian surface, which is irreducible, which is the Jacobian of some curve of genus 2 having an order 5 automorphism. And you have some linear, some automorphisms of this equation given by multiplication by this matrix that has order 5. So you have C2 when you quotient by this lattice that's order 5, and in C2 you have some eigenvalues, eigenvectors, some eigenvectors corresponding to this this diagonal matrices, and these will give you some constant vector fields on your abelian surface that are preserved up to multiplication by some constant by this order 5 automorphism of the curve. So what Cosgrove says is that this chassis 11 equation is given by one of these vector fields that are preserved up to some constant by this order 5 automorphism that you may compactify both this variety in C3 with its vector field as this abelian surface with one of these almost invariant vector fields. So the point is that there is some geometry. Every time we have this sort of absence of multivaluedness is because there's some geometric setting that's enabling us to have it as these very restricting conditions that we would like to understand better in higher dimensions or in other settings, and that we currently don't. But there's some very beautiful examples around that are very interesting to look at and interesting to meet when you start studying this. So thank you very much.
Any question?
How did people guess on this abelian surface? Is this a totally different surface that was controlled from the equation?
Okay, so suppose you knew my result before, our result. So you say, well, oh, this is another equation. Okay, so you can find, so Cosgrove's result is really by it's computer assisted. So you need the computer to do all the calculations. He needs the computer, and the problem that Chassis stated that integrate this equation, it should be integrated by elliptic functions, was dormant for 90 years. So it involves some computer. So the geometric picture is clear, but linking this geometric picture to the equations themselves takes a lot of calculations. So I don't know how Chassis guessed, but what you can do is you can, if you believe the theorem or that something like the theorem might be true, then there's two vector fields, not just one. So you may ask, where's the other one? And then hopefully we'll find a vector field that commutes with the first one and that gives you the second vector field that's preserved. And actually you can calculate, and then you can see that there's a second vector field that it's also homogeneous to some degree, has the same first integral, and that commutes with the first one. So you can start refining your guess about the first integral. And then the fact that the first integral has degree 10 says that if you multiply by a fifth root of unity every variable, you will remain within the same level set. So you're guessing that it should be an abelian surface, and it should have some order 5 automorphism. So this is the only one that does. So there's guesses that narrow down the possibilities. But at the end, you need some computer to prove things. Yes?
I have some potentially really speculative, certainly speculative thing to just recall. So I had some really interesting conversations about 5 or 6 years ago with Terry Tao about these Pain-Lavie equations. So one thing that people have observed is if you look at KdV or the Kadomtsov-Petvishvili equation, there are various reductions from these 1 plus 1 completely integrable systems that lead you to Pain-Lavie. And then later there was work by Ablowitz and collaborators that showed that there's something called self-dual Yang-Mills equations, which they in turn reduce to these 1 plus 1 dimensional integrable systems, which then go down further. So there may be some sort of a, 25 years from now, master theory related to insights around self-dual Yang-Mills that explains somehow all of this combinatorial mystery. And I don't understand any of it, but I find it really speculative and interesting because there are these massive structures that appear to have really rich geometric and algebraic properties that may explain some of this in some synthetic way. So, I don't know, but I thought it was a really cool conversation.
Yes?
Yeah, I would have a question about your result with all the primes.
Okay. What? The previous one?
Yeah, just previous. So I wonder whether this last case where you have these stripes at your supposed to happen very often or very rare?
No, it's very rare. It's very, very rare. There's some, in order for this to happen, you need some Diophantine things that should be solved in the space of equations, and they're very, very special. So. No, it depends. It depends very much on the family. So in general, being not having multivaluedness would be some closed condition. And then depending on the family that you choose, this closed condition might be something like a lattice. But in other settings, this closed set might be some fractal set. And so that depends very much upon the context. So if you fix some numbers, some integer numbers, some of the equations might be deformed and preserve these numbers. And so it depends.
Any other question? In this last equation that you mentioned, this three-dimensional with this first integral,
yes.
Also it has some fibers which are singular. And
yes.
then you can desingularize this, and then you would get, but now not an elliptic surface, but some kind, perhaps rational surface.
Yes, in general, the complexity descent. So the interesting one are the non-singular ones, because they are this is a philosophy more than an explanation, that the more interesting functions arrive with non-singular varieties.
Okay, so we thank